For over a century, the global power grid has operated as a single, synchronized physical machine. Every time you flip a light switch, you are tapping into the momentum of thousands of enormous iron rotors spinning in unison across the continent. This physical momentum is governed by what engineers call the swing equation. It describes a simple relationship. When a sudden disturbance strikes the system, like a lightning strike or a sudden spike in demand, the kinetic energy stored in those heavy spinning masses naturally absorbs the blow. We call this property inertia. Because these iron rotors are so incredibly heavy, they resist sudden changes in speed. That physical weight acts as the grid's natural shock absorber, allowing it to smooth out the electrical ripples and keep power flowing without interruption. Modern wind and solar farms operate completely differently. They connect to the grid using fast-acting power electronic converters. These are highly efficient digital systems, but they lack a massive underground iron rotors of the past. They have virtually zero physical mass. By replacing heavy coal and gas turbines with lightweight renewable tech, we are systematically stripping the physical weight out of the power grid, and in doing so, we have accidentally removed its natural defense mechanism. Without that heavy iron to act as a buffer, the grid is completely exposed to a new phenomenon: Subsynchronous Oscillation, or SSO. Because modern power electronics process electricity at microsecond speeds, they can occasionally react too quickly to minor grid fluctuations, creating a volatile feedback loop. In July 2015, grid operators in Xinjiang, China, saw exactly what happens when that feedback loop spirals out of control. A routine disturbance at a local wind farm triggered a runaway subsynchronous oscillation. An invisible wave of fluctuating power surged out of the converters and traveled 300 kilometers across the transmission lines. When those invisible electrical waves reached a traditional thermal power plant, they perfectly matched the mechanical resonance of the plant's hardware. The electrical flutter excited violent torsional vibrations in the equipment, twisting the solid steel turbine shafts until they physically cracked. To prevent further destruction, protective relays slammed shut, instantly ripping 3 large generation units offline and plunging the region into a sudden 1,280 megawatt blackout. Similar mechanical fractures have since been recorded in Vietnam and Russia. We have moved beyond the era of simple power outages. Microscopic digital errors in a remote wind farm now manifest as physical force capable of shattering solid steel hundreds of miles away. A cracked turbine shaft is only the localized symptom of a much larger vulnerability. Because the grid is highly interconnected, these low-frequency oscillations can synchronize across vast distances, forcing entire geographic regions to swing against one another. Engineers call these inter-area oscillations. In the western interconnection of North America, there is a specific pattern known as the North-South B mode. During an event, generators in British Columbia and the Pacific Northwest will literally oscillate out of phase with the generators in the desert Southwest and Southern California. This chart shows the erratic, overlapping voltage angles recorded across the network during an actual instability event. By mapping these readouts in real time, engineers can measure exactly how violently the northern and southern halves of the grid are pulling against each other. The grid operates as a single, dynamic physical entity. A localized flutter in one state can easily ripple outward, triggering a continental electrical earthquake. To defend against these continent-wide swings, grid operators have to map the network's hidden vulnerabilities. They do this by acting like seismologists, intentionally injecting controlled shocks into the system and measuring how the ripples propagate. At the Chief Joseph Dam in Washington state, operators conduct these tests using a massive 1,200 megawatt dynamic braking resistor. By slamming this colossal load into the grid for just half a second, they deliberately ping the entire western interconnection, revealing the exact shape and frequency of the resulting oscillations. But these physical field tests exposed a critical flaw in how we monitor the grid. For decades, engineers relied on root mean square, or RMS, modeling to predict system behavior. RMS models calculate averages over time. They are completely blind to the hyper-fast sub-cycle electromagnetic dynamics of modern solar and wind inverters. The tools built to monitor the heavy iron grid simply move too slowly to see the ultra-fast oscillations tearing it apart. We needed a new way to observe the grid before it breaks. To catch these anomalies, investigators have to abandon the old averaging models entirely. They are now pivoting to microsecond-level data, analyzing the grid's electrical behavior fraction by fraction, looking for the exact moment an oscillation begins. A single regional grid now connects thousands of individual wind and solar installations. Identifying one malfunctioning inverter amidst that complexity is a significant engineering hurdle. To solve this, researchers are deploying machine learning algorithms like transfer component analysis. By sifting through massive batches of raw, microsecond-level grid data, the algorithm can recognize the distinct signature of an open-loop resonance, instantly isolating the specific wind farm causing the disruption. In this weightless environment, these software analytics have become as essential to grid survival as the high-voltage transmission lines themselves. Finding the bad data is only half the battle. Pinpointing a malfunctioning wind farm doesn't fix the underlying physics. The grid is still dangerously light, and it has permanently lost its heavy physical shock absorbers. The solution isn't to build more iron rotors. It is to program virtual synchronous generators into the power grid. These are advanced digital controllers designed to inject virtual inertia back into the system. This graph illustrates exactly how it works. A standard inverter outputs a wildly oscillating wave during a disturbance. A virtual synchronous generator calculates the exact physical weight and swing resistance of the old iron turbines, digitally injecting a counter-torque to oppose instability. By mimicking a heavy spinning mass, this digital illusion cancels out dangerous oscillations before they break physical hardware. The transition to renewable energy requires us to strip millions of tons of heavy metal from the power grid. To survive that transition, we have to extract the mathematical properties of those old iron machines and program their ghosts directly into the digital controllers of tomorrow.